All right, last video for the module. We have already talked about Gibbs's free energy back in module 6. And so we've already seen this equation right here. Remember, Gibbs free energy is a product of the ideal gas constant, and this is the value that we normally use in this equation in order to get everything to cancel. The temperature in Kelvin, and then the natural log of K, which is the equilibrium constant. Now, again, we've already talked about the fact that delta G is negative for spontaneous reactions and it's positive for non-spontaneous reactions. So what that means is that if it's negative, that means that it is emitting energy. And in the form of electrochemistry, emitting energy means that I could use that reaction to power a galvanic cell. Okay? If delta G is positive, that means that it requires energy. Remember, it's not going to run on its own. It's got to have energy put into it to make it go. And so that means that this reaction would need an electrolytic cell to take place. Okay? I can relate delta G to redox reactions with this equation. Again, you've already seen this in your reading, but N is the number of electrons, and it has to be balanced. So like if you had 3 electrons in one half reaction and 2 in the other, then you would have to have that balance. So you would have to use 6 so that you're gaining and losing the same amount. F is Faraday's constant, which is going to be a constant that relates your energy and your number of moles and your volts. And then the sum of the half potentials, which you learned how to calculate back in module 9 as well. So we will work through example 10.8 so you can see how this works. They ask us to calculate the potential, delta G, and the equilibrium constant for this reaction. So you've got 2 Ag plus, I believe it was zinc, plus zinc yields 2 Ag plus zinc 2 plus. So the first thing when you work a problem like this is that you've got to figure out the reduction potential for the cell. Okay, so I've got to look at the half reactions. If I take Ag plus to go to Ag, and I find that on the standard reduction table, you're going to see that it's 0.7991. And then if I take zinc, and I convert it to zinc 2 plus 2 electrons, that's going to be 0.763. Again, you know how to find those values off the table. That's not anything new. So when I add those together, the standard potential for the cell is going to be 1.562. Okay, so there's the potential for the cell. Then it asked me to find delta G. Well, since I know E, and I know N, and I know Faraday's constant, this is the formula that I'm going to use. So I'm going to use delta G equals negative N. Well, the number of electrons, I've used 2 here. And if I was going to balance this, I'd have to multiply this equation by 2 also. So in this equation, for this particular example, N is going to be equal to 2. Then I'm going to use Faraday's constant, joules per volt mole. And then the reduction potential, 1.562 volts. Okay? So, plug and chug type of problem. When you plug that in there, you're going to end up with the delta G equal to negative 3.014 times 10 to the 5th. Okay, so very negative reduction potential. Then if they ask you to find equilibrium constant on top of that, then you're going to have to take that and you're going to have to use this equation. So if I have delta G equals negative RT natural log of K, this goes on this side, negative 3.014 times 10 to the 5th joules per mole equals the ideal gas constant, negative 8.314 joules per mole Kelvin. Temperature, well, the temperature, I'm going to, we're doing things under standard conditions, which is 25 degrees Celsius. So that means the temperature is 298 times the natural log of K. Okay, so when you work all this through and end up solving all that out, you should end up with a K of 6.460 times 10 to the 52nd. Very, very large equilibrium constant. So we know that it is going to go almost to completion, which probably doesn't surprise us considering that we did have also such a large delta G. Okay, I don't think you will find these problems difficult. Again, it's a matter of looking at the table, finding the reduction potential, and then plugging the appropriate values into the problems. So you should be good with that.